So, good morning, everyone. Today we're going to be having a discussion on heat transfer by conduction, looking a little more in depth in conduction as it applies to several systems. And I'm guessing today we're only going to get to a discussion on steady state systems, which means next week we will be discussing the transient conductive heat transfer concepts. So I will most likely be making some adjustments to module 8. However, it won't have any effect on your assignments, homework 8, the synthesis assignment, and the quiz. We're kind of assuming we probably wouldn't get to this.
Sorry, God.
So today we're going to be talking about heat transfer by conduction. So recalling from Tuesday, I can state that my heat flux, or even a differential heat flux, can be approximated as the temperature gradient that exists times a constant known as the thermal conductivity of a substance. Keeping in mind, this is for a one-dimensional system. For a multi-dimensional system, we have to consider the heat flux as some function, okay, but now considering the partial derivatives in the x and y and z planes, which we can simply summarize as the thermal conductivity times the gradient of temperature for each plane. Now the good news, for this class we're really not going to get into multidimensional systems, primarily because in order to do it effectively, it takes a lot of numerical solutions, because the analytical solution of solving for the gradient function is extremely complicated. And so a numerical solution is a lot more simple and effective, but it's would take a couple weeks to really get into effectively. And so for the purpose of this class, I neglect that discussion. If you're interested in learning more how to look at, multidimensional systems, come talk to me in office hours and we could have that discussion. But for right now, we're going to stick to just one-dimensional systems. And so, looking at this one-dimensional systems, we can simplify our expression, which we've done in the past with Fourier's law, stating if I'm looking at a simple material, I can identify the conductive heat transfer through that material as the thermal conductivity times the surface area times the temperature gradient over this material and divided by the material thickness. I can also rewrite this expression as the temperature gradient over what's known as R, where R is the thermal conductive resistance of our material. And so for conduction, R is simply equal to delta X over K times A sub S. And this should give you units of kelvins per watt. Or if you're looking at English units, your units will be hours, degree Fahrenheit per BTUs. Now, we can also, if we want to, we're not going to spend too much time considering it, We can also calculate thermal resistance due to convective flow or convective heat transfer. And so we can define a convective thermal resistance as simply 1 over the heat transfer coefficient times the surface area, which once again give you the same units. So the question then becomes, why is this useful? Well, when we want to consider multi-component materials or composites, as they're better known, use of thermal conductive resistance becomes extremely helpful. So let's take a look at an illustration of what I mean. Let's say I have a wall, but instead of being just made up of one material, it's made up of 3 materials. And each substance has its own thickness. And I know on this side of the wall, I have some temperature, and on the another temperature, an ambient temperature on the outside of the wall. So then my question then becomes, will the heat transfer rate be the same between each layer? So what do you think? So I'm going to call on Pratik. What are your thoughts? Do you think the heat transfer will be the same or different between each of these layers in my wall?
I think it depends on delta x1, delta x2, delta x3. If they are equal, I think, and if the cross-sectional area is also equal, it's going to be the same. I think it's going to depend on the change in the length for each term.
Okay, you bring some interesting points. So yeah, so you're interested in, well, what's the delta T? Are they going to be the same or different? What about the surface area? The way I've drawn it, the surface area will be the same. Anybody want to help him out? How about Mitch? What are you thinking?
I think it depends on the type of material. Like you said yesterday, copper holds a lot of heat rather compared to something like aluminum.
Okay. So you guys have some good thoughts. I like it. I appreciate the interaction. So now I will say, let's say the inside is going to be, I don't know, a high temperature. Let's say it's 80 degrees. Inside it's a kitchen. You're cooking up a storm. And outside it's 20 degrees. Now, I will say that most likely there's going to be, depending on the materials, different delta T's in the walls, or for each layer. However, there's a couple interesting ways that we can consider it. And the most effective way of analyzing this system is using what's known as a resistances in series model to evaluate the heat transfer through the composite wall. And so what that means is I know each of these layers, has a particular thermal conductive resistance. And so what I can do is I can model that resistance like so. Right now I have some resistance 1, some resistance 2, some resistance 3. And depending on the nature of the air, I can have some convective resistance on the inside and on the outside. And what it allows me to do is for my system, or it's actually be a combination of conducting or convection, I could say my heat transfer is simply can be calculated as the temperature gradient over the whole system, or Ti infinity minus To infinity, divided by the total thermal resistance, where R total is R convection 1 plus R1 plus R2 plus R3 plus R convection 2. And since I know that the total resistance is equal to the sum of the individual resistance, and my total delta T has to be the sum of any temperature gradients that exist within our materials. What I could find is that in addition to the heat transfer rate being calculated as the temperature gradient over the total resistance, it's also equal to the gradients over the resistance in each layer. And what that tells us is that, well, if we have heat transfer going from one direction or the other, the heat transfer has to be the same through each layer. So I'll repeat that. The heat transfer, right, must be the same for each layer.
Even for different materials?
Even for different materials.
That's crazy.
And actually, as I've written this, there's probably going to be 2 more delta T's. There's a convective delta T, and then there's on the inside, and there's a convective delta T on the outside. What that means is the temperature here at the surface is going to be different than the ambient. And the temperature here on the surface is going to be different from the ambient. So just for completeness, somebody might ask me about that here in a second. And so it's a useful way of analyzing systems or composites. One, because it allows you to consider the differing materials and being able to analyze them in a way that, for the most part, is fairly straightforward. You know, you're applying that resistance in series that we see a lot in circuits. And 2, it allows you to keep in mind, well, if the heat transfer is going from the inside to the outside, the rate has to be the same, right? Think of it in terms of an energy balance. If the heat transfer is going from inside to outside, anything that is passed through, let's say, layer 2, has to have come from layer 1. If this doesn't hold, then you have an accumulation of heat somewhere. and your system's not going to be at steady state. So let's take a look at an example together. So for this example, I have a furnace wall constructed of 4.5 inches of a silane brick with a thermal conductivity of 0.089 BTUs per hour per foot per degree Fahrenheit, backed by 9 inches of common brick, which has a higher thermal conductivity of 0.8 BTUs per foot per hour per degree Fahrenheit. If the temperature of the inner surface of the wall is 1400 degrees Fahrenheit and that of the outer face is 170 degrees Fahrenheit, what is the estimated heat loss through the wall, as well as the temperature at the interface between the silane brick and the common brick? So I'll give you guys a minute to jot this down. All right. So let's take a look at this example together. Now, as always, I definitely recommend that you draw problems, if at all possible. So we've got silane brick, and then we got common brick. The dimensions here are 4.5 inches and 9 inches. I was told that the temperature on the inside wall, which I'm going to assume is the silane brick, is 1400 degrees Fahrenheit, and that at the outside wall is 170 degrees Fahrenheit. The thermal conductivity of the silane brick was about 0.089 BTUs per hour per foot degree Fahrenheit. Of the common brick was 0.8 BTUs per hour per foot degree Fahrenheit. So with this in mind, we can determine the heat loss through the wall and the temperature at the interface between the silane brick and the common brick. From our discussion just a little bit ago, I can state the heat transfer through the wall is equal to the total temperature gradient through the composite wall divided by the total thermal resistance, where I can find the total thermal resistance as a sum of the resistance through the silane brick plus the resistance through the common brick. So what we need to find out are the two resistances in this wall. Here, I'm going to try to start zooming out more so that you guys don't lose material. So the resistance 1 is therefore delta X over K times A. Did I say how big this wall was? I did not. So that means we'll have to consider a basis for our area. So what basis would you like to use for our area?
One square foot.
There you
Yeah,
go.
that's always nice.
Not always possible. You make a basis of 1 or 100 depending on the problem. So with that in mind, our initial thermal resistance, R1, is simply the thickness, or 4.5 inches divided by 12 feet, divided by the thermal conductivity, or 0.089 BTUs per hour, foot, degree Fahrenheit, times the area, which is 1 square foot. So I get a value of approximately 4.21. Check my units. Feet squared goes away. And so I'm left with hours, degree Fahrenheit per BTU. So what I need to find out next is my second resistance. Same equation, but now I have 9 inches. Here, if you want to make this a little neater, I'll express this down. .8 BTUs per hour, feet, degree Fahrenheit, times our 1 square foot. So with this calculation, I have approximately 0.94 hours, degree Fahrenheit per BTU. This means that my total resistance is just the sum, or approximately 5.15 BTUs, hours, degree Fahrenheit per BTU. Is everybody following along okay? All right. So now that we have our total resistance, we can solve for a heat transfer rate because our total temperature gradient is simply 1400 degrees Fahrenheit minus 170 degrees Fahrenheit, or approximately 1230 degrees Fahrenheit. And so our heat transfer rate is 1230 degrees Fahrenheit over our total thermal resistance of 5.15 hours, degree Fahrenheit. Come on. Per BTU. Or approximately 238.8 BTUs per hour. Or since the basis was 1 square feet, we can also say that since really soft 4 was flux, so it is technically per foot squared. All right, so we were able to determine the heat transfer rate based off the temperature, the information given, applying our resistances in series model. Based on the thermal conductivities, we were able to determine the resistance in each layer. The total resistance was simply the sum, and thus, with that in mind, we were able to solve for our heat transfer rate using our simplified expression of delta T over R total. Now, the last thing the question asked was the temperature between these two layers. So you know it has to be somewhere between 1400 degrees Fahrenheit or 170 degrees Fahrenheit. And so to find the temperature between the two layers, we have to consider the modification of our expression. And say, well, that heat transfer rate has to be the same between each layer. So we have to consider essentially finding delta T1 or delta T2. And with that in mind, we can find the temperature in the middle. So which value would you like to solve for? Delta T1 or delta T2?
T1.
T1, okay. So I know by this expression, delta T1 has to equal Q times R1, or 238.8 BTUs per hour, times R1, which was approximately 4.21 hours, degree Fahrenheit per BTU. We do that, we get approximate delta T of 1005 degree Fahrenheit. And so since the temperature gradient over that first layer is 1005, that tells us the T that we're solving for is 1400 degree Fahrenheit minus 1005 degree Fahrenheit. Or approximately 395 degree F. So what do you guys think? Hopefully that one isn't too bad and you're able to follow along. Okay. All right, so let's think of a different system. Now, instead of having a multi-composite layer, as we've identified, how can we consider a system that looks like this? Where I have a wall. I got some inside temperature, some outside temperature, but instead of having the wall be composed of several layers that look like this, I have a wall or composite that has differing materials stacked on top of each other. So the question then becomes, how will our heat transfer differ when we have multiple components in parallel? So, Alyssa, what are your thoughts?
Maybe it won't necessarily have to be the same rate, because it's not going through one to get to the other during the transfer.
Mm-hmm. You are correct in that regard. Right. Another way I can think of this is, right, let's say I have, it wouldn't actually be like that, it would be more like this. So let's say I've got a wire And it's a copper wire. So I'm going to paint it orange. So you're right in that if this is a copper wire, right, and these other layers of insulation, the majority of the heat transfer, thermal and electrical transfer, if that was the case, would happen in this system, right? So I will definitely agree and argue that heat transfer will be different for each layer in parallel. However, following the use of our resistances in series model, I can still continue to use a resistance model, but now I can consider a resistance is in parallel. What I can find is that the total resistance through this section or slice that I have here is going to be the sum of the inverses of each layer's resistance taken to the inverse, right? So just like solving for the total electrical resistance in parallel, we can sum the total thermal resistances in a similar fashion, right? And so if I had a system that looked like this, right, where this is T in, this is T out, I can essentially, when I recommend, right, is draw some form of equivalent circuit. And then you can essentially label each resistor and from that, identify a total resistance. So for this system, it would be R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 to the inverse plus R5 plus 1 over R6 plus 1 over R7 to the inverse. And so when you look at a multi-composite wall, you can identify which systems materials are in series with each other, which materials are in parallel with each other, and identify a total thermal resistance such that to solve for a heat transfer, you just have to consider the total gradient over that total equivalent resistance. Now, as Alyssa mentioned, through each layer that's in series, the heat transfer rate will be the same. However, when you have layers in parallel, the heat transfer rates will not be the same, right? Just as I had shown earlier, I could have a highly conductive layer between two insulating layers, and so the majority of that heat transfer will occur through that material with a high thermal conductivity. Any questions on that? Is that clear? Is there any questions that you have for follow-up? All right, so go ahead.
It will be the same for each vertical section, essentially.
Yes, so if I had essentially what I would have is a delta T1 here, I can consider a delta T2 here, a delta T3 here, and a delta T4 here.
Okay,
And so the
thank you.
heat transfer for each of these 4 sections will be the same. However, if I break it down in terms of what I see in terms of R2, R3, R4, those will not be the same. All right, so let's take a look at an example. And this one's going to be a little complicated. So I have a 3-meter high and 5-meter wide wall consisting of long 16 centimeter by 22 centimeter cross-sectional horizontal bricks, separated by 3 centimeters of plaster. There are also 2 centimeter thick plaster layers on each side of the brick and a 3 centimeter layer of thick foam on the inner side of the wall. If the indoor and outdoor temperatures are 20 and -10 respectively, and assuming the inside and outside heat transfer coefficients are 10 and 25, what is the steady state rate of heat transfer through the wall? So this one is a little more complicated than the last example. I will go ahead and give you guys some time to write this information down. Okay. So this is what I'm going to do. Let's take a look at this example. And what we can do is I'm going to go ahead and draw out this problem for you. And then I'm going to shoot you all into some breakouts to solve for a few things. So the brick, I'm going to call red. The plaster, I'm going to make gray. And the foam, I'm going to make pink. So we've got foam, plaster, and brick. As always, the temperature on the inside is 20 degrees C. The outside is -10 degrees C. We know this layer is 3 inches. We know the plaster is, let's see, 3 centimeter layer thick. So this is going to be a layer here and a layer here. This thickness will be the same. This will be 2 centimeters. And the brick is going to be 22 centimeters wide. And so we have an interesting system. I know my H on the inside is 10 watts per meter squared Kelvin. H on my outside is 25 watts per meter squared Kelvin. That makes about sense. More wind on the outside than the inside. So I want you guys to take a look at this. And I'm going to send you to breakouts for a few minutes. And I'd like you to come up with an expression for our total thermal resistance. So our total equals what? I'll give you guys about 3 or 4 minutes to do that in some groups. How's it going, guys?
Good. We're calculating, we just split it up into 4 verticals, and now we're calculating the resistance for each vertical.
Perfect. I'll give you guys a little more time to work.
Hi, Dr. Lopez.
Hey, Claire, how's it going? How's your group doing?
Well, we were discussing how to separate everything out first, and then just rewriting down all of the things that we missed while we transferred here. I took a screenshot of everything, so I
Okay,
have
well,
all
I
the.
can share it with you guys if it helps, but if you got a screenshot, that works.
Mhm.
Dr. Lopez, I do have a question.
Go for it.
Is it possible for these resistances to show up more than once in this expression?
Technically, yes, right? Because the plaster is kind of everywhere. And so you'll
Mhm.
find
Right.
that, like, because you got 2 layers of plaster, right, that are literally the same layer.
I see.
But yeah. So yeah, you'll find out that there's a couple that will keep popping up.
Okay, that makes sense.
All right, I'll let you guys work for a little bit.
All right, thank you, Dr. Lopez.
How's everybody going? How's the group doing?
Kind of confused, to be honest.
Okay. So what are you confused about?
Well, I'm looking at it based on the drawing you gave us as kind of 4 vertical sections,
Mm-hmm.
and finding the total resistance between each section, adding those together to get an overall total. So then for the first 2, you just have series,
Yes.
right? And then parallel and series. So for the parallel, could you just call it like, say, call it R3 for that section, like you have the first, second, third resistors going down, sum the inverses of those and take that to the -1, and that would be your resistance for that section?
You are correct.
Okay. I think I was getting confused because we're not actually solving for it. So I was trying to find out.
No, you're fine. And if you want, you guys can spend a little bit and start solving for some of the layers. We'll do that as a group, but if you guys want to work a little bit further, go for it.
I do have a question about like if you're solving for that first section of foam, would you say like your delta X over, it wouldn't be, we don't have a K, so it's not the K times.
Did I not give you a K for the foam?
You gave us H for.
Well, K of the foam is 0.055 watts per meter Kelvin.
Oh, I just didn't write it down.
Wait, no, hold on. K of the, I was reading a different problem. The foam is 0.026 watts per meter Kelvin.
Okay. And then do we have a K for the plaster?
The K for the plaster is 0.22.
22, same units.
Yes, watts per meter Kelvin.
Cool. I think that was the only thing I didn't have. And
Okay, no
then last question, I think you wrote the width of the foam section. Did you write 13 inches? Is that?
For the foam?
3 inches. I was trying to read the picture.
The foam is, let's see, 3 centimeters thick. The wall is, well, there's a couple ways you can do this. The wall is 3 meters by 5 meter high, but we're looking at a small subsection of that wall. And so the easiest way to do this is basically solve it for the small subsection and correct it for the total area of the wall.
Oh, okay. Okay, I think that.
Because it's like a wall, and so there's like repeating units of bricks, and so if you if you were gonna try to do essentially the heat transfer of the entire wall, you would have so many things in series and parallel, it would be just kind of overwhelming.
Gotcha. Okay. Thank you.
You're welcome.
Yeah, I'm gonna try the first one and see what that gives us.
How are you guys doing?
We're doing decent. We tried to split up the problem into a series of parallel and like parallel series. So our original plan was to do the resistance of the foam plus plaster 1, and then a parallel of plaster brick plaster, and then the plaster 2 to the left and right of the brick. Is that a correct way to approach it, or?
Yes.
Yay.
Okay, cool.
Yeah. All right, good.
All right, so then do we still use the area of the entire wall, so 15 square meters, or the
I
area
would
of
not
each individual?
recommend it. Right.
Yes,
I admittedly I drew a small subsection of that. So it's best to consider the area of the small subsection as identified between like a brick and then the plaster layers around
Yeah.
it, and then correct for the area at the end.
Okay, cool. Thank you.
You're
Yes,
welcome.
sir.
Oh, up here.
Hello.
On your
How's it going, guys?
convection.
We think we've got an equation for R total.
Okay.
But is that for each individual brick?
Yes.
Okay.
Essentially, we're looking at a small subsection of this wall.
Okay.
Surrounded around a single brick.
So in terms of the entire question, are we going to have to find how many bricks are in the wall and then multiply the heat for each brick by those number of bricks?
What we would probably do is just solve for the heat transfer of this subsection and then correct for the area.
Okay.
It's because then to identify how many bricks, it can get a little messy.
Yeah, that's kind of what I was thinking.
Yeah. All right, so you guys seem to be on the right track. I'll let you work for a couple more minutes.
Good.
Okay, that would make sense.
Yeah. And then what about the foam? What did you say for that?
I said the area of the foam was 15 meters squared.
Okay, I see where you're coming from.
And then same for the plaster layer on both sides.
Yeah, I have that. Okay.
So, Dr. Lopez, we came up with an R total equation
Okay.
that we think is correct, and then we're just kind of discussing how to calculate from there with all of the different
Pieces in this problem.
numbers.
Yeah.
Yeah. What areas we're supposed to be using and all that good
Yeah,
stuff.
so the way I developed my solution is I essentially identified the area around like a single brick, similar to what I drew.
Mhm.
And then I solved for the heat essentially transfer rate through that subset of area, and then I just corrected the area for the entire wall
Okay.
at the end.
Okay. So can I kind of explain to you what our
Go for it, of
our
course.
equation is? Okay. So for our equation, we started with the convective R for the inside. So the 1 over HIAS. And then we have plus, and we divided that section that you drew into 4 vertical sections. One that's just the foam, one that's just the plaster. The third one is plaster, brick, plaster. And then the fourth one is just plaster.
Yes.
So with that, we have R1 plus R2, and then plus 1 over R3 plus 1 over R4 plus 1 over R5 to the negative 1.
Mm-hmm.
And then we have plus R6, and then plus the 1 over H out AS.
Yep. Very good. So then the hard part is trying to figure out, okay, how do I define each of these R's?
Yeah.
Okay, we'll do that here in a second. So give me 60 seconds and we'll all come back.
Okay, awesome.
see, everybody should be coming back in the next 20 seconds. So how'd it go in your groups? Hopefully you guys were able to come up with the expression and maybe get started on doing some calculations for the resistances. Okay. So let's see how well it went and how well you did. So for our total, what you should end up getting was R associated with the convection on the outside, or inside, excuse me, plus and resistance associated with the foam, plus resistance associated with the plaster layer, plus, all right, this layer is the tricky layer because it's essentially resistances in parallel. So you have 1 over another layer of plaster, plus the resistance associated with the brick, plus another resistance associated with plaster, plus a resistance associated with plaster again, and then the convection on the outside. So were your groups able to come up with an expression similar to this? Oh, -1, excuse me. Yes or no? All right, I see somebody shaking their head. So then the tricky part comes with, okay, trying to identify all of these resistances. One of the sticking points that I've seen with this is essentially because the wall is a 3 meter by 5 meter wall, right? So that the area of this is 15 square meters. However, the brick is only 16 centimeters by 22 centimeters. And so the question then becomes, well, based on this, what are the dimensions should I be using for this wall? Correct? And well, if let's say this section is 22, this section should be 16 centimeters. And if the plaster layer here is 2 centimeters, then this layer should be 3 centimeters on the top and bottom of the brick. That means this whole section that I'm looking at is only approximately 22 centimeters long, right? So this subsection is essentially only 22 centimeters in height, length, whatever you want to use. And so what that means is we're only looking at a small subsection of this wall. And so the best way to identify the total heat transfer to the wall is to simply identify the area of this subsection and go from there. And so for the area of the subsection, what I have is a 22 centimeter length, or a 0.22 meter, times the z dimension, which we don't have. So to make it easier, I'm going to assume it's just 1 meter, or a 0.22 square meter subsection of this wall. And so this will essentially serve as my basis for the calculations. And so with that in mind, there's a couple things that you can do. You can calculate essentially the number of repeat units in the wall and then do all your calculations associated with heat transfer, or you can find your heat transfer rate for just this subsection and then correct for the area at the end. So for this problem, I'm going to use the latter method. And so what I need to do now is identify values for each of these resistances. So let's start with the convective resistance 1 on the inside. This is simply 1 over H times A, or 1 over 10 watts per meter squared Kelvin, times my area of 0.22 square meters, which gives me a value of approximately 0.455 kelvins per watt. The next value I need to identify is the resistance in my foam layer, which should be a delta X over K times area, which the thickness of that layer is 3 centimeters or 0.3 meters. The thermal conductivity, as provided in the problem for my foam, is 0.026 watts per meter Kelvin, and the area 0.22 square meters. So I get a value here of 5.24 kelvins per watt. And then I have my plaster layer. Now, one thing you can identify is the plaster layer here and my plaster layer here are essentially the same layer. And so that tells me my resistance value should be the same, or R plaster 1 equals R plaster 4, which equals a delta X over Ka once again, or 0.02 meters divided by the thermal conductivity of the plaster, which is 0.22 watts per meter Kelvin, times the area, 0.22 square centimeters. Or approximately 0.413 kelvins per watt. Next, I have to identify the resistances in plaster 2, plaster 3, and the brick. Once again, the resistances in plaster 2 and 3 are going to be the same based on symmetry. Now, this is where it gets a little tricky. In this layer, my thickness is going to be 22 centimeters. And so my thickness now is 0.22 meters. My thermal conductivity is still going to be the same based on the plaster, 0.22 watts per meter Kelvin. But now my area is going to be different than the original layers because my dimensions have changed. Now for these, since they're 3 centimeters around the brick, the area is going to be essentially 0.03 times 1, or 0.03 square meters. where I get a value of approximately 33.3 kelvins per watt. Lastly, I need is the brick, which once again, the same conductive resistance expression. Now the thickness here, once again, is going to be 22.22 meters. My thermal conductivity is going to be 0.72 watts per meter Kelvin. And my area is going to be the length of the brick, or 16 centimeters, times our basis of 1 in the z direction, or 0.16 square meters. Or approximately 1.91 kelvins per watt. And finally, the last one we need is our convective resistance on the outside, which is going to be 1 over HA, or 1 over 25 watts per meter squared Kelvin times our area of the whole area section that we're interested in, or 0.22 square meters. Or approximately 0.18 kelvins per watt. So a lot of calculations, a little repetitive, but now we have all of our resistances that we can plug into our total expression. And so plugging all this in, I can say my R total is equal to my convective layer on the outside, or 0.455 kelvins per watt, plus my foam, 5.24 kelvins per watt, plus my 2 plaster layers, 2 times 0.413 kelvins per watt, plus looking at now my areas in parallel, I have plaster layer 2, plaster layer 3 in the brick. Since my plaster layers are the same, I can simply say it's 2 divided by 33.3 kelvins per watt, plus 1 divided by 1.91 kelvins per watt to the inverse, plus that final convective layer on the outside, 0.18 kelvins per watt. So yes, a little bit of a lengthy problem, but if we do this, we should get a value let's see what I could come up with. Approximately 8.41. For our total resistance. Now with that in mind, I know my delta T is 20 degrees Celsius minus a negative 10 degrees Celsius, or 30 degrees, which tells me my heat transfer rate is approximately 30 degrees Celsius divided by 8.41 kelvins per watt, or about 3.57 watts. Now this is per 0.22 square centimeters of the wall. To correct and find my total heat transfer rate, It's simply my 3.57 divided by my wall area, right? So it's almost like a pseudoflex times my actual wall area, which is 3 times 5 meters. And I get approximately 243 watts.
Are you going to change the 30 degrees Celsius to Kelvin?
It doesn't matter since it's a delta degree. A delta Celsius and a delta Kelvin are the same.
Right, right.
So with that, we have our total heat transfer rate. So a little bit of a lengthy problem to say the least, but hopefully you see kind of how to break the problems out and do it kind of step by step. Are there any questions on this? All right, if not, we'll go ahead and stop here. And as always, if you guys have questions, feel free to reach out to me via email. We'll go ahead and finish up the last little bit of this on next Tuesday, and we'll jump into transient heat conduction pretty quickly. And thank you guys for your attention. Take care, have a great day, and as always, have a great weekend.
You too.
I have a question.
Go for it.
For the exam, are you gonna have a test review like you did previously?
Yes, I will. I believe it's on the syllabus the day of the next exam review.
I'll be sure to check that out. Thank you, Dr. Lopez.
No problem. Take care.
Have a great day.
You too.
Thanks, Dr. Lopez.
Of course.